Hey everyone, welcome to this explainer where we're going to fundamentally break down how Qualcomm's Project Dragonfly blueprint plans to solve literally the most critical hardware bottleneck in artificial intelligence today. Our goal today is to faithfully translate and explain exactly what's inside these source slide materials so you can see how the physical architecture of AI is about to change forever. We are looking at a massive paradigm shift, so let's dive right in and map out exactly how it works.
So here's our agenda for today. We're hitting 6 key areas: Agentic AI and the memory wall, proximity as performance, the paradox of two HPCs, dissecting the Dragonfly architecture, the full-stack ecosystem, and finally, the economics of power. All right, let's get into it.
Section 1, Agentic AI and the memory wall. To get why the hardware is changing, you really have to look at the massive shift happening in software workloads, specifically what's coming our way in 2026.
Take a look at the clear visual split here. On the left, we've got where we are right now, Q&A AI. It's pretty straightforward, right? A single input goes in, a single output comes out, and it leans heavily on brute force training. But look over on the right. 2026 and beyond is the era of agentic AI. We're talking about the year of the agent. The whole process becomes this wildly complex web of continuous, multi-step reasoning, dynamic tool use, and recursive logic. And the output? It's completely exponential. This means we desperately need a shift from brute force learning to an ultra-efficient execution infrastructure that can actually handle rapid, non-stop context switching.
And this explosive growth, it exposes a massive root bottleneck called the memory wall. Check out this graph on the left. AI model parameters are literally exploding, growing exponentially and completely outpacing GPU compute capacity. See that red shaded area? That is the wall. It means during the decode phase, our absolute fastest, most expensive calculators are just sitting there, totally idle. Why? Because they're waiting for the data, the books, to be delivered. To generate just one single token, the system has to fetch hundreds of gigabytes of model weights. Plus, it's constantly managing the KV cache, which is basically the system's memory notepad, and that just keeps expanding with every single word generated. So the compute isn't actually the problem here, the delivery is.
Section 2, Proximity is performance. Beating this memory bottleneck takes a totally radical shift in physical chip design. And the secret sauce? Proximity.
Right now, the industry is basically split into 3 totally different philosophies to handle inference. First, NVIDIA. Their approach? Just widen the highway. They use high bandwidth memory, or HBM, to pump up the physical bandwidth. It totally works, but man, it is insanely expensive and complex to manufacture. Then you have Grok. They're all about instant speed and zero jitter using SRAM. They keep all the data right there on the desk, but the catch is it severely limits memory capacity, making massive models really tough to run. So what's Qualcomm's play? Well, they argue we shouldn't widen the highway at all. Instead, their philosophy is near-memory computing using high-bandwidth compute, or HPC. They're essentially moving the factory next door, trading a little bit of peak baseline speed for absolutely massive capacity and basically zero travel time.
The whole genius of Qualcomm's approach is wiping out what engineers call the transit penalty. Think about it. Moving data across long motherboard traces or wires physically wastes an immense amount of energy and creates built-in latency. The physical medium of transit is literally the enemy of efficiency here. Whether you're looking at radiative wireless through the air on the left or those long trace interconnects on a motherboard on the right, the real solution is just removing that physical distance entirely.
Section 3, the paradox of two HPCs. As we dig through these blueprints, you're going to see the acronym HPC a lot. Funny enough, it actually points to 2 completely different technologies united by one physical truth.
Okay, check out these dual paradigms of HPC. On the left, Domain 1, human-body communication. This is wild. It uses the low-frequency capacitive coupling of actual human skin as a secure zero-wire conduit for wearables. No wires at all. Then, on the right, Domain 2, high-bandwidth compute. This uses 3D stacked silicon and microscopic vertical interconnects for AI cores. So one is all about secure wearables, and the other is about smashing the AI data center memory wall. But they both prove one massive point. Absolute maximum efficiency only happens when you eliminate the physical distance data has to travel. Like we said, proximity is performance.
Section 4, dissecting the Dragonfly architecture. Let's look at how this proximity principle physically builds Qualcomm's big counteroffensive, internally codenamed Project Dragonfly.
So let's demystify what HPC actually looks like in hardware. On the left, you've got your traditional setup, a compute die and a memory die separated by a long bus. It's kind of like sending raw parts down a massive long assembly line. Takes forever, right? But look at near-memory computing on the right. Qualcomm is basically building the workbench right inside the storage warehouse. They run lightweight computations directly underneath the high-capacity memory, using these mind-blowingly microscopic vertical channels called TSVs, or through-silicon vias.
And here's the beautiful 3D stacking behind the Dragonfly philosophy. You have the LPDDR memory layer right on top. That's what holds those huge datasets like model weights in the KV cache. Right beneath it, fused together by those vertical TSV pathways, is the compute XPU layer. By actually running localized operations instantly at the data source, only the finished, essential processed results get sent outward. It's an absolute game changer. It drastically cuts down on data movement and completely bypasses that traditional memory wall we talked about earlier.
Now, this whole multi-die interconnect schematic gets its name from nature's most efficient flyer, the Dragonfly. And it totally makes sense. Just like the insect, this hardware architecture is all about independent modules working together with incredible efficiency. It prioritizes extreme energy savings, modular flexibility, and decentralized coordination over just brute force monolithic power. Section 5. A full-stack alternative ecosystem. Look, we all know that taking on a dominant monopoly in the data center takes a lot more than just building one really fast standalone chip.
Qualcomm is actually building out an entire full-stack ecosystem resting on 4 distinct pillars. Step 1, you've got the C1000 CPU orchestrating the computation. Step 2, HBC XPUs handling the heavy acceleration. Step 3, open standards routing the network. And Step 4, a modular software translation layer that ties the whole shebang together.
Sitting right at the heart of this ecosystem is the C1000 Orion CPU. Just look at the sheer scale of this component. Over 250 custom chiplet cores cranking at 5 GHz. But the really strategic part is its DNA. It's actually leveraging low-power smartphone heritage to act as the ultimate traffic cop for these complex, simultaneous agentic requests. It routes the heavy lifting over to the GPUs and the rapid generation tasks straight to the HPC specialists. And check out the note at the bottom. This efficiency is so compelling that Meta has already officially signed on as an anchor client for their next-gen server fleet using the C1000. Next up is the software and networking strategy. On the left, you see NVIDIA's closed ecosystem. It's basically a walled garden, forcing vendor lock-in through their proprietary CUDA software and NVLink networking. But on the right, this is Qualcomm's Open Bridge counteroffensive. They're jumping on Open UA-Link and Ethernet standards to network hundreds of chips together. On top of that, they dropped $3.9 billion to acquire a company called Modular. Modular acts like a universal translator, letting developers run their models on literally any hardware without having to rewrite all their code. They are quite literally tearing down the walls. Bringing it home with Section 6, Power Economics and the Future. Let's dig into why this fundamentally matters to the hyperscalers, the folks who actually foot the bill to run these massive data centers. When you start looking at HPC metrics, there's this one truly staggering number, an effective bandwidth of 133 terabytes per second. You're probably thinking, wait, how is that even physically possible with mobile memory? Well, it's all in the nuance of the calculation. HBM measures the actual physical volume of data shoved through a wide bus, but HPC, it measures the effective speed you achieve by just avoiding that bus entirely. The data processed locally plus the massive amount of time saved by having zero transit mathematically yields this unbelievable effective bandwidth. And that brings us to the ultimate economic reality charted right here, total cost of ownership. When you're operating at gigawatt data center scale, the upfront capital cost of the hardware, that's almost nothing compared to the ongoing operational power costs. You are practically paying for a whole power plant. These massive multipliers tell the real story. By using 3D stacked proximity, Qualcomm gets 6 times more bandwidth per watt than HBM, 200 times more capacity per watt than SRAM, and double the performance per watt of legacy CPUs. They are radically slashing the operational power needed to generate every single token.
So, as we finally leave behind this era of brute force, single-chip speed races, and start embracing system-wide, power-efficient architecture, the whole concept of the data center is transforming. By effectively moving the factory next door, the transit penalty is just gone. So the big question we have to ask ourselves is, as agentic AI demands exponentially more from our hardware in the coming years, who will truly control the underlying infrastructure of the future? Thanks for joining me on this explainer. I hope you found it as fascinating as I did. Keep analyzing, and I'll catch you in the next one.